You got it? I'll begin with a word of prayer. Dear Heavenly Father, we thank you for the weekend and the nice weather. Just pray you be with us today. Help us to glorify you again, Lord, in what we do. We thank you, Lord, that whatever righteousness we have, Lord, it's your righteousness and not our own. We're thankful for that, Lord. In your name I pray. Amen. Let's see here. We didn't cover this stuff, did we? Oh well. This stuff was fun. But we did not cover it, so let me go on here. Come on. Let me just talk through a couple of problems here before I turn it over to you guys. So this problem here, what are we supposed to do? We're supposed to show it's increasing or decreasing, I suppose. So if you try a couple numerical test points, you can pretty quickly see it's decreasing, right? Because you're going from like 0.4 to number I can't figure out the decimal of that quickly, to number I still can't figure out the decimal of that quickly. But anyway, you can see they're getting smaller if you compare them to sort of standard benchmarks. If you take the quotient of a n plus 1 by a sub n, you get this. But then, see, 2 to the n plus 1 is 2 to the n times 2. 4 to the n plus 1 is 4 to the n times 4. Then what do I do? Multiply. Oh, I got a 2 to the n up here and down there, so I can cancel it, right? And that leaves me this times that. If I make the denominator smaller, we get a larger quotient, right? Larger fraction. And once I do that, I can break it into two pieces because we can break up a sum in the numerator. The 4 to the n's cancel over here, and you get 1 over 4 to the n plus 1. And as you can see that let's see, that is at most what? When n equals 1, it's what? It's 1/16. So a half plus a 16th, otherwise known as 9/16, right? So less than 1. So there you have it. It's a decreasing sequence, right? And you can see that it's bounded above by 2/5, the first thing. It's bounded below by 0 too, right? Because this is a positive sequence. So by the bounded monotonic sequence theorem, the limit of this is what? It's decreasing, it's bounded below by 0. What's that? Mm-hmm. Oh, well, I'm trying to show that this is less than 1 because I know that that's the same as showing that a sub n plus 1 is less than a sub n, which is to say that if I can make this less than 1, that shows it's decreasing. Now, if you don't like this, you could, of course, take like the function 2 to the x over 4 to the x plus 1, differentiate it, and try to show the derivative is negative. I don't know if that would be easier or harder. I think it might not be helpful here because I think when you take the derivative, you kind of face the same inequality that you do to start with. So I'm not entirely sure calculus will help you here much directly. Let's see here. Another one I should look at with you guys. Not that one. Where is the one I'm on? There's one I'm looking for in here, guys. Sorry, I should have told you to take your Dramamine. Where's the one with n factorial to the n? This one has an idea in it which you might not think of, perhaps. I mean, there's a method of calculation here which is kind of worth talking about. So here we're supposed to show that 2 to the n over n factorial goes to 0 by establishing that 2 to the n over n factorial is less than or equal to 4 over n. All right, and I think that's for n greater than or equal to 2. Yeah. You need n greater than or equal to 2. If you look at n equals to 1, I don't think it's true, actually. Is that, well, no, it's true. Okay, it's true for n greater than or equal to 1. Now, why would this be shown to go to 0 if we can establish that? Do you guys understand why that is? What theorem did we have? Remember? If we have a sub n less than or equal to b sub n less than or equal to c sub n, and this goes to 0, and that goes to 0, it implies that the limit as n goes to infinity of b sub n is also equal to 0. This is the squeeze theorem, right? So it's kind of obvious that 0, right, is less than or equal to 2 to the n over n factorial. And it's less obvious, but it's also true, that that's less than or equal to 4 over n. So if you can establish that this is smaller than that, well, this goes to 0 as n goes to infinity. That goes to 0 as n goes to infinity. So that implies that the limit as n goes to infinity of 2 to the n over n factorial is 0. Right? So let's walk through this. So what is 2 to the n? 2 to the n is 2 times 2 times 2 times 2. How many times? Right, n of them. How many factors do I have down here? I have n of these, right? So n, n minus 1, n minus 2, all the way times 2 times 1. So what do I look at? What I'm looking at here is just rearranging things. I got 2 over n minus 1, 2 over n minus 2, 2 over 3, 2 over 2, 2 over 1. So what do I say? I say each of these has a ratio of what? Of 2 by a number which is greater than or equal to 2. What does that say? Right, each one of those is less than 1. So it follows that, why is there a 4 here? Oh, because of this guy, right? This guy, that guy right there. So this guy and the bookends here remain to give us the 4 over n, because all of this is less than the product of 1 times 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 1. You get the idea. And so there you go. I think this idea might be tough to think of by yourself, but now you've seen it, right? So maybe you can do this in similar problems as well, right? Do I have any other ones like that in here? Let's see here. That's a little bit different. I mean, it's kind of, that one was kind of similar, but not the same. All right. Well, anyway, that was the one. I guess we'll come back to a calculation like that again when we get to it in chapter 12. I mean, there are questions that are asked about whenever you run up a question that's about like n to the n and n factorial. You might need to do some thinking, like I just showed you on that problem. All right. For the quiz tomorrow, though, I'm mostly interested that you have your basic limits down and you can apply L'Hopital's rule with confidence and competence to a few simple problems, right? Maybe just 2. So any questions about the homework in particular? I've covered the ones I wanted to do for sure. Mostly just that one I just showed you, this one. So you guys understand the homework completely? You know, I paid good money for this sticker, and I was hoping it would have an effect, but what? What? Okay. Interesting.
So you might quiz on improper integrals?
No, I will not quiz on improper integrals. I sent an announcement out. I decided against that. I will test improper integrals in the quiz after fall break. So pretty much all we'll cover this week after we get past today is just improper integrals. Yep. Yeah.
Could you go over number 37?
Sorry. Woo. All right. 37. 11-2. Let's see here. Let me get rid of. We have the natural log of n plus 2 over n plus 2, right? And we're supposed to calculate the limit. Oh, wait a minute. We're supposed to determine the boundedness in mono... I'm not sure I can say that word right now. Monotonicity of the sequence with a sub n is indicated. So this is my a sub n, I suppose. Whew, man, like a moth to a flame, I just want to apply L'Hopital's rule to this thing, you know? All right, so if you want to decide whether this is increasing or decreasing, this looks like a job for calculus. So what I would say is let f of x, I'm trying to decide whether it's increasing or decreasing. It's monotonic if it's either increasing or decreasing. You pick one or the other, right? You can't have both. You're like, I want to live in a world where things are increasing and decreasing. Well, that's fine, but then everything's constant for you. So, I mean, if you want everyone to have the same things and no one to have anything different, then I guess you want a world where everything's increasing and decreasing. Let's not live in that world. Let's see here. F of x is this. This is the function which corresponds to the sequence, right? At whole numbers, and then I differentiate it to see what happens. Okay, fine. F prime of x is equal to, or if I was smarter, I could do direct inequality arguments perhaps. But the trouble is, the reason I can't just do direct inequality without a lot of work is because the logarithm is increasing, but n plus 2 is also increasing, and the question is which one of them wins, right? There's a couple different ways I can come at this, but let me just calculate. So this is minus 1 over x plus 2, quantity squared. What? Oh. Yeah. Yeah. I did the product rule because I'm weird. Fine, here I'll put it back together. You guys will be happier. You quotient rule people. 1 minus the natural log of x plus 2 divided by x plus 2 squared. Now you happy? Okay. Is that positive or negative? Well, at x equals minus 2, something funky happens, right? But thankfully, we're only interested in what? We're only interested in x greater than or equal to 1 because we're interested in the sequence that corresponds to this function. All right, so really the question is this less than 0? I mean, okay, so we can draw a number line for this, just to organize my thinking. When is this 0? This is equal to 0 if what? One equals to the log of x plus 2, right? If I take the exponential of both sides, that gives me e is equal to x plus 2. In other words, x is equal to e minus 2. So the critical number is e minus 2, which is what? Two point 2.717 minus 2, it's about 0.7, right? So the points I care about for the sequence are past that, right? Like 1, 2, 3, 4, 5, 6, 7, like here, right? And so forth. So is this function less than? What is the log? So the log is, This is all going to be negative. The function is negative there because you plug in whatever you want. If you plug in E, for example, this gives me, oh, E is a bad choice. I don't know. But if you plug in a specific number bigger than this, you'll get something negative because the log is bigger than 1 over there. All right? So the point is, f decreasing on e minus 2 to infinity, which implies that a sub n is decreasing for n greater than or equal to 1 by calculus. Now, if you don't like my way, you could do direct arguments with inequalities. But that's up to you. I don't want to do it that way. I mean, you could work your way from the no. And what am I supposed to do here beyond this? I'm supposed to just determine if it's increasing or decreasing, and then what else? That's it? Yeah. Which one? This was what? Number 37 in section 2? Was this one of the recommended ones? How did I do it when I did it before? Or did I not? Did I skip this one? Oh, 11.2. Yeah, I have trouble with math. Let's see here. No. Oh, look, yeah. Oh, I'm sorry. I've been very boring. I gave you the same argument again. I'm sorry. Ah, yes. Sort of the same argument. But does it make more sense when I say it now? Yeah. It looks a little different here, but it's the same thing I'm really saying. Anybody have another way to do it? Mr. King? Do you have another way to do this one?
No, if I had to directly prove it, I have to use 1 over the inequality over 2.
1 over what?
I mean, I used to do with the exponential one, like the 1 plus.
Yeah.
I used to go like 1 plus 1 over n to the n power that is an increasing sequence.
Uh-huh.
And I had to use the Bernoulli inequality.
Oh. Ah, yes, see, yes. We have not imported that yet. Sorry. Yes. Although Bernoullis have been dead for some time, we should know by now, but you know. Yeah. There's a place in my thesis where Bernoulli's numbers come into play. I don't understand it. My advisor did it. Like, what are Bernoulli numbers? Okay. I mean, I've seen them in some homework somewhere, but they come up with certain sequences or series. All right. Sorry. Other questions? All right, let me just go down the list here. This one's kind of important. So here we define a sequence by just continually adding a thing, right? So you start out with 1, then you add r to it, then you add r squared to it, and you keep doing this, all right? So the nth one is 1 plus all the way up to the sum of r to the n minus 1 power, right? And so, like if you put r equals to 1, the nth thing in the sequence would just be n, right? So the limit as n goes to infinity there would be infinity. So that one would diverge. But if you had r not equal to 1, right? You could look at this. You could look at Sn, which was this by by definition. You okay? Oh, I mean, you're okay, but I don't know about the bottle. It's okay. If we multiply r times Sn, we get. See how this works, guys? R squared, r cubed. See how that goes? Everything's matching here. Like there's a pairing between everything except for this r to the n and the original 1, right? So when you take the difference of these two, what's left over is just the 1 and the r to the n there. So what this gives us is that Sn minus r times Sn is 1 minus r to the n. And then you can do algebra, factor out the 1 minus r. And that gives us actually just a straight up formula for the nth term in the sequence as that, right? And then you guys tell me, how does that go if we think about this thing? This wasn't part of the problem, I guess, but what happens to the limit as n goes to infinity of 1 minus r to the n over 1 minus r? We could say that that's equal to the limit, right? As n goes to infinity of what? Of 1 over 1 minus r, right? Minus the limit as n goes to infinity. Oh, sorry. Factor out the 1 over 1 minus r, right? There's no n dependence there, is there? I mean, so this is the sum of two things, this fraction, and then minus r to the n over that, but I can pull that out of the limit, supposing it exists. When will this limit exist? When will it not? This right here. Remember we talked about limit as n goes to infinity of like c to the n? What was it? It's 0 if the absolute value of c is less than 1. It's 1 if the absolute value of c is equal to 1. Oh, sorry, if c is equal to 1. And it does not exist if the absolute value of c is greater than 1 or minus 1, right? Minus 1 to the n as n goes to infinity goes plus minus 1, 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 plus minus 1. It never goes to one thing or the other, right? It just keeps oscillating. But if the absolute value of c is less than 1, then it goes to 0. Well, that's the same thing here, right? C is just r in this example. And so like this does what? This goes to 0, provided what? R is less than 1. Absolute value of r, yeah. Absolute value of r is less than 1. So what we have then is 1 plus r squared plus plus r to the n minus 1 goes to 1 over 1 minus r, provided the absolute value of r is less than 1. And actually otherwise it diverges, right? This is kind of fun, right? So if you have, for example, 1 plus a half, plus a fourth, plus an eighth, plus a 16th, plus a 32nd, plus a 64th, plus 128th, and so forth and so on forever and ever, what do you get? Not 0, no. 0. I mean, this term goes to 0, that's true, but what's the sum go to? 2, right? Yeah, 1 over 1 minus 1/2 is 2. Or if you like another example of this, 0.999999999, oh, you get the idea, is what? That's 0.9 plus 1/10 times 0.9. Oh, I'm sorry. Let me write that another way. Fine. Stupid 1. Fine. 1. Okay, so that's 1 plus... no, that's still not what I want. Oh, man. I'm sorry. I've worked myself into a... I need to like multiply this result by a to get what I want nicely. That puts an a here, all right? So like a in this one is 0.9, and then you've got 1 plus 1/10 plus 1 over 100 plus 1 over 1,000 plus da da da, I think. Oh, I'm still wrong, aren't I? I don't think I'm, well, it's not really what I wanted to write though. I wanted to say 0.9 plus 0.9 over 10, 0.9 over 0.9 over 1,000, like that. In other words, it's 9/10, you know, plus 9/100ths, and so forth and so on. So what would that be? That would be 1, excuse me, it would be 0.9 divided by 1 minus 1/10, aka 0.9 over 0.9, also known as 1. So there you go. There's the proof that 0.99 repeating is 1. Brought to you by the theory of convergent sequences. I'm misbehaving, of course. What are we doing right now? I mean, I'm not entirely misbehaving. This was a homework problem. But this thing we're starting to do is series.
Yeah.
This is the province of chapter 12. But series are defined in terms of sequences, so it's not like these, you know, these are related things. More on that later. Any questions about anything in particular? You guys got no questions. I just need one. I'll put this thing away. Maybe that'll help. Well, let's see here. This one, you know, there's another way we could have looked at this one. I mean, this shows it's decreasing, right? So we could do kind of a sneaky thing here. We could calculate the limit directly, right? And how would we do that? I think just one application of L'Hopital's rule does it, right? Why would that be interesting? Well, since we've already gone to the trouble of showing that this is a decreasing sequence, right? What did the bounded monotonic sequence theorem say? It said that this was also equal to the greatest lower bound of the sequence, right? Of the range of the sequence. So if you use that theorem, I can tell you that a lower bound for this sequence is, the greatest lower bound for this sequence is 0. Right? And so like this one, I have 0 is less, I think it's actually not equal to, but less than the log of n plus 2 over n plus 2. And that's less than or equal to what? It's a decreasing sequence, right? So a decreasing sequence, the upper bound for a decreasing sequence is just the first thing in the sequence, right? Which is what? A sub 1 log of 3 over 3. So there you go. There's how to bound that sequence. So we can, if we can use the bounded monotonic sequence theorem, we can sometimes save ourselves some direct argumentation. If you're looking for one where we determine the boundedness directly, here I'll look at number 14. Try to do something a little bit simpler. Here we have a sub n equals to n minus 1 over n. Let's see here. I would rewrite that as 1 minus 1 over n, right? So it's fairly clear what happens as n goes to infinity. This goes to what? 0, right? And it's also pretty clear that this is a decreasing. Oh, I'm an idiot. Yeah, 1. Sorry. I was thinking of the 1 over n. Duh. Anyway, that goes to 1. So it starts at what? At 0. And then it's a half, 2/3, 3/4, so forth, right? So it's increasing, actually. This is an increasing sequence. And so 1, by the bounded monotonic sequence theorem, is the least upper bound, right, of the range, for what it's worth. But anyway, you can argue directly that let's see here. I would say this is a, I'm sorry, I'm losing track of my thoughts. Is this decreasing or increasing? I think you could see an plus 1 is equal to what? 1 minus 1 over n plus 1. I don't think I need any kind of trick here. I can argue this one directly. This is what? Excuse me. Other way, right? So if why is that reasonable? I made the denominator what? Smaller, right? Which makes the fraction bigger, but I'm subtracting it, right? So that makes the net expression smaller. So that's why I say that this is larger than that. But this, of course, is a sub n, right? So therefore, a sub n is increasing.
So when you say you make it smaller or bigger, you're adding one or subtracting one?
I could be doing a lot of things. How can you make a fraction smaller or larger? You know, if you want to make it larger, make the numerator larger, or make the denominator smaller.
So you're just manipulating it.
Uh-huh. You know, some functions like the exponential we know are increasing functions, right? So like if I have, for example, 2 less than 3, you know, is 2 less than 3? Sure. So that also tells me like e to the 2 is less than e to the 3. There's stuff like this you can do. But I guess, you know, if I had n is less than n plus 1, that implies that e to the n is less than e to the n plus 1. There's things like that you can do. Those are also true with logs, because logs are increasing. Or square root is an increasing function. I can take the square root of inequalities like that, provided I'm looking at something non-negative. Oh, so I didn't finish my thought here. What are the bounds? So it's increasing, right? What's its bounded? So if it's increasing, what's that mean? We just put them in order. A1 is less than A2 is less than or equal to A3, and so forth and so on, right? So that means that A1 serves as lower bound, right? So what's my A1 here? Yeah, so we have 0 less than or equal to 1 minus 1 over n, and the least upper bound is 1.
So are we only working with
Well, we're working with real numbers and natural numbers. I mean, sequences, a sequence is a function from the natural numbers to the real numbers, right? Remember? So what is a sequence? A sub n. A is a function, really, from the natural numbers to the reals, where a of n we denote by a sub n. This is, you know, a sequence is a function, whose domain is n, exactly. So you can also look at sequences of complex numbers if you just replace the r with c. You can look at sequence of functions if you want.
why do you start with 1, not like -1?
Well, you could start with something else. Like, in some sense, this starts at 0, you know? But, well, I don't know, like I said, we typically start with 1, and you can adjust, you can write many of the theorems we're writing for, you know, starting somewhere else if you wanted to. But 1 is just convention.
The natural numbers are normally greater to be 1 and above. I mean, some people think they're
Yeah, some people say the natural number start at 0.
Yeah.
How about you, Mr. King? Natural number start at 0 or 1?
I see a lot of 0 and a lot of 1.
Ah, yeah. You could go either way. But I will insist that it's 1 just to be annoying.
But for a sequence, you can have a A0. Essentially, because...
Right. Excuse me. Here, let's, well, for lack of a better idea, let me work some L'Hopital's rule problems. Since you guys are a little, unless you have another question.
Yep. 11-1, number 23.
11-1, number 23. Right. here we're looking at the set S equal to 1/10, 1/1000th, 1/100,000th, and so forth and so on. Typical thing being 1/10 to the 2n minus 1 power. Okay, so that's like 10 to the third, 10 to the fifth, 10 to the odd power. All right, so forth and so on. And it tells us epsilon is equal to 1/10 to the k power. Well, let me write it. This is 1/10 to the k power, where k is something bigger than 1. We're supposed to find a number s that satisfies the assertion made in Theorem 11.1.4 for s and epsilon is given. So the theorem says what? It says m is less than or equal to s is less than m plus epsilon. M is the greatest lower bound of s, right? So here, and this is number 23, yeah. So what are you trying to do here? First of all, what's the greatest lower bound of that set? Yeah, it's 0, right? So first of all, we would identify m equals to 0. So what am I really trying to do is I'm trying to solve 0 less than s, right? Less than or equal to 1/10 to the k, right? Now s is what? Little s is an element of the set, right? So it's not just any old real number, it's a real number of a very particular form. What do the elements of the set look like? Well, they told us what the arbitrary element looks like, right? They gave us it right here. So what we're really trying to solve is 1/10 to the 2n minus 1 is less than or equal to 1/10 to the k. Right? This is the m plus epsilon. All right. This looks like a job for the logarithm. So we have 1/10 to the 2n minus 1, right? Is less than or equal to, we're trying to solve this inequality, 1/10 to the k. And these are positive, right? You know, the log is an increasing function, right? It preserves inequality. So I say take the log of this inequality. What does it give you? I guess you could take the log base 10 if you want, but I'm going to take the natural log because I don't feel like talking about log base 10, and it's not a big deal. So this gives me minus 2n minus 1 natural log of 10 less than or equal to minus k times the natural log of 10. In other words, minus 2n minus 1 parentheses less than or equal to minus k. Yep.
Is it supposed to be less than or equal to or just less than? Started from the beginning, it looks like it's kind of small.
Oh, yeah, less than. Sorry. Anyway, we're trying to find such a k, so. Do you guys understand what I just did there? Why there's a minus? What? Yeah? Okay. So like this is, for example, this one's 10 to the minus k, right? Okay, anyway, so cancel the logs from both sides, and then, so what I want is what? I want, multiply this by minus 1, what do you get? You get 2n minus 1 greater than k. So I can choose, right? What am I trying to find here? Yeah, but what am I'm trying to do what? I'm trying to find, find the s. So if I choose n subject to that condition, it should work. Remember what was getting here. K is greater than or equal to 1. Right, so I can just let s equal to 10 to the 2n minus 1, where 2n minus 1 is greater than k. That's probably not how they want me to write it. They probably want me to write it in terms of k. Let's see here. So I could let s equal 10 to the k plus 1. Or s equals to 10 to the k plus 2, I guess. I'm supposed to take, I mean, if I want it to be an element of this thing, it has to be an odd power, right? So if I happen to be given, a, I'm still not saying this right. I don't know. This is the point in class where I have no energy left. Anyway, I need to meet this condition, right? Certainly, if k is odd, I just take, I can't take k plus 1 anyway, right? I need k plus what? K plus 2. Otherwise, it's not in the set, right? If k is, if k is odd, think about it, then, like, for example, so if this was, for example, if this was 5, then if I do k plus 2, I get 1 over 10 to the 7th. That's a number that's between that, the fifth power and the 7th and 0. But I have to add 2 if k is odd. If k is even, what do I have to do? I need to make it, I guess just k will work, k plus 1, right? Yeah.
I mean the power in k or is.
I mean, this, I was modifying that, there. Sorry. Look, you can draw a number line. This is really not that complicated. 0 is here, right? You pick something in here, 1 over 10 to the whatever, 10 to the k, right? All I'm saying is that there's a point either right here, 1 over 10 to the k plus 1, k even, right? Or there's a point over here, 1 over 10 to the k plus 2, if k happened to be odd. If k happens to be odd, then that means that this is also in the set, These are not equally spaced, but this is, I don't know, let me stop talking about the problem. This problem's not interesting. The point of this problem is to try to get you to think harder about greatest lower bounds and the meaning of that theorem. The theorem is geometrically obvious. Do not be confused by it. Do not let this theorem have its way with you. Yes. You should just... It's a pesky, obvious theorem. All right, well. Sorry I didn't do anything interesting today. I guess that's it. Tomorrow a quiz, and then we will do improper integration for the most part, okay?